beta, IB is your IC ka. Oh, your IC. So, multiply mo ng beta tong 4.7 and 1.2. Ano, nakuha mo, Mr. Maranyon? Wala. Nagsusolve naman, nakikita ko, oh. Kanina. Glean. Any answers, Glean? Ano, Mr. Maranyon, walang sagot? No response? Glean? Right, ano, ingay. How about Mr. Marcaida? May sagot na?
Sir, 1.07 microampere yung sa ICQ, sir.
Micro or milli?
Milli. So,
Milliampere. May 0.07 milliampere. How about your VCEQ? Nakuha niyo lahat yan, 1.07? So your VCE, dito ka lang mag-KVL. So VCC minus your ICRC. And then your ICRE or your IERE, wherein IC is equal to IC as well. So we have your VCEQ at 3.69 and your ICQ at 1.07. Next, we have yung voltage divider bias circuit, which is known as your exact analysis. So from this, magkakaroon nga tayo ng yung ETH and then your RTH, just like Thevenin's rule. So for the voltage divider analysis or the exact analysis, so yun nga, mag-voltage divider tayo, VCC, taking now yung equivalent na your ETH, VCC times your R2 over the sum of your resistor 1 and resistor 2 taken onto these 2 points. Kaya as katumbas the circuit, so magiging ganito siya for your voltage divider. So we solve your ETH and then your RTH is simplified as the parallel connection of your R1 and R2. Tapos we can now proceed with yung KVL on the base to your emitter loop and then your collector to emitter loop. Yeah, IB is now your ETH minus your BBE over your RTH tapos your IERE, pero we have relation of beta plus 1 times your RE is your IE. I beta plus 1 times your IB is your IE. Kaya yan. O eto, so ano yung RTH parallel ni 39 and 3 times 3.9 over the sum ng 39 at saka 3.9. So, pag na-solve nyo na yon, magkuha na tayo ng IB, loop lang from the base to the emitter loop, and then your VCE is your collector to your emitter loop. Pag nakuha niyong ETH,
2, sir.
2 volts. How about your RTH?
3.55 kilo, sir.
Okay, 3.55 kilo ohm. So, given na yun, so you can now proceed with the KVLs on the 2 loops, base to emitter, and then your collector to emitter loop. So, wag na ko na tama yung ETH, RTH. Okay na, madali na lang. So, ayan. While kapag, okay na, since nakita ko na nakuha niya yung RTH, RTH, so simple na lang. Gaya lang din naman sa past problems yung gagawin. Di bale, you can take this for your correction. So, that is for the exact analysis. While kapag, eto naman tayo, kapag we have now your approximate analysis for a voltage divider by a circuit. So, we can take your VB now as yung parang VTH as well, your R2 times VCC times this over the sum of the two resistors. And it should be that your beta RE is much greater or equal to times your times 10 of the resistor 2. Tapos solving now your BE is your BB minus your BE. Kung ba ito kasi yung sa beta times your R is must be equal or greater than times 10 dun sa second resistor, wherein your I is BRE and then ICQ is most likely equal din kay IE. So yun lang for approximate analysis, pero this is hindi naman minsan ginagamit, so doon tayo sa exact analysis. Pero for yun lang for approximate analysis, take note that your beta RE is should be equal to 10 times dapat dun sa resistor along now malapit dun sa base or going to the ground. Okay, so anything goes. Circuit, pero paano kapag yun nga PNP transistor, sabi ko baliktarin lang natin yung mga conventions. So on this case, ito ng BBA, baliktarin niyo din yan ha. Dito lang kasi magkakaiba minsan yung sa libro. O tignan nyo, BCC is also taken as negative. PNP transistor. So if you take that, minus IERE plus BBE, pero dapat ito na pati yung si BBE is na iba. Kumbaga dito kasi ganito naman na yung sa sign, pero pag parang taken mo as ganun lang yung sa sign, basta baliktarin nyo din. Mababaliktad din yung convention pag sa PNP. Since gano'n naman na yung sa bias negative na din doon. Tapos minus your IBRB plus BCC equal na to 0. So gano'n lang, baliktarin lang halat ng sa conventions even dito sa may BBE. Yung sa pinakita kong una kanina. Kasi doon sa derivation. Pero eto, after tama din naman eto, just taken kasi talaga nakuha ng BCC at negative. Ayun na to for voltage divider bias. Ito ang isang maganda. So, paano naman kapag we are asked for a design operations? Oh, given that your ICQ at operating is already 2 milliamperes and then your BCEQ at 10 volts. Given your beta at 100, determine now your R1 and then your RC. So, ito for voltage divider bias. Paano? Paano natin solve now your R1 and then your RC? Voltage divider still. So may calculation naman tayo on how to solve your VTH. Pwede nyo gamitin doon. Solving now your BB. Anong value ng R1 and then your RC? So pwede nyo i-take out sa voltage divider by taking now your ETH or your VTH as your 18 times your R1 times your R2 18 over R1 plus R2. Tapos yung sa RTH, yun din, parallel nga ng R1 and then your 18. And actually, you can take a relation on there, tapos you can play. Or pwede agad na kunin natin yung BB, which is yung BBE plus your VE, since ma-solve na natin. Given na tayo ng ICQ. Or dito, parang nagkuhan ka agad ng along sa collector to emitter loop. Pwede agad yun. So result now your R1 and then your RC. R1 is 86.52 and then your RC at 2.8 kilo ohms. Determining now VCEQ pag ganitong configuration, try VCEQ and then IEQ, or simply your VCE and then your IE. Okay, this configuration is actually a miscellaneous configuration. It is known as your emitter follower circuit or the common collector configuration. So for this case, to solve now your VCEQ, then your IEQ, we need first to solve your IB. O paano dito si IB? KVL tayo dito. KVL para solve yung IB. So anyone can answer. Okay. Dito lang din naman yung KVL. Plus dito na yung next. Or pwedeng pag ganun. So ano yung BCE? Nakapag-solve na ba? About your IE? Sure, may sagot na. Derwin. Ano?
Sir, ano, 45.734 milli. Yun, sir.
Yung IB. Pero,
Yes, sir.
how about your BCEQ and IEQ?
Wait lang, sir.
Since may IB ka na, so beta plus 1 times beta plus 1. Yun lang din yun.
Four 4.162 milliamperes.
Yes,
Sir.
tama. So, next, yung BCEQ na lang. So, si BCEQ, kahit dito na yung sa KBL. Yung dito. So, minus BCEQ minus your IE RE. Tapos, plus your VE. Meron dito yung 20 volts. So, masolve mo si BCEQ. So, pwedeng pa ganun, minus 20 plus IERE plus BCEQ.
Sir, 11.676 volts.
Kung 11.67 or 11.68 volts. Good. So, yan yun. How about kapag ganito, determine the currents IE and IB and the voltages BC and BBE. Ito naman, common base configuration dito. Common base configuration. Kumbaga, paiba-iba lang mga orientation. So, tignan natin. Same pa rin naman yung KVL, KCL lang talaga ginagawa. So, tignan natin. How about ito? IE and then your IB. Dito kasi para mga single stage lang din talaga bibigyan. Hindi kayo bibigyan ng mga multiple stages parang ginagawa dati sa klase. Pag board exam kasi hindi naman talaga ganun. Single stages. Pero iba-ibang orientation minsan ng circuits. Baka imagine mo, try mo lang i-mirror ito. I-mirror mo siya. Para mas madali. Or simple KVL nga lang din siya. Diba dito? O pag ganun ka na KVL. So, 4 minus, so plus minus, minus BBE, and then plus it's calculated now. So, divide mo lang ng 1.2, mas-solve mo na si IE. Tapos knowing that your relation ng IE tsaka ng IB, beta plus 1 times your IB is your IE, mas-solve natin si IB. Sa BCE naman, so, and BCE, di ba dito yung sa BCE? So, yung sa loop mo, kunin mo dito, punta mo pa ganon. I go into the output. BCE, BBE,
Sir, yung IE 2.75 milliamps.
yes, 2.75 milliamps. So, how about now your BCE? And then your BCB. Okay.
4.1
Pansin nyo na,
sir.
4.1 yung,
BCE sir.
nice, sino yung sumagot? Yung
Naitan sir.
sumagot? Good. So, how about your BCB? Ako, 4.1.
3.4 volts, sir. 3.4.
3.4. Medyo malapit naman kung sa 3.51. So, how about sa iba? Saan kayo nahirapan? L. Kahit buuin mo nga yan, buo. Kasi at DC naman kanyang mga yun, open circuit. Buuin mo lang yung KVL, tama? So, si BCB, collector to base, parang dito lang. Ayan. Collector to base, eto lang. So, ayan nga, 3 point, di ka, malapit naman yung nakuha ni Mr. Juan, around 3.51. O si Glenn, lumipat na ng area. Makakasagot na din siguro. Ano, Glenn? Uy, Glenn. Oh, ayan. 4.1 and then 3.51. Okay, for diba, madali sundan lang. Kung ba KVL lang, buuin nyo lang din. Buuin lang KVL. KVL lang yung pinaka-solution niya. So, we have more miscellaneous configurations just like ito. So, mga ito pa. Ito kasi 2 stages na siya. Pero most of the time talaga naman, so far, wala pa naman mga 2 stages. Ito, pwedeng single stage kasi ito. So, para pag ganito naman yung configuration na lumabas. So, ito sa calculation, your VB is actually now your R1 over your R1 plus R2. So, parang nagbo-voltage divider ka lang din. Multiply now your VEE negative. So, to solve now your VE is equal now to your VB minus your VBE, which is your 0.7. Plus IE, syempre dito lang siya, IE. So, your VE minus your VEE over your RE. Tapos kapag given ka ng Zener diode, ayan, for Zener diode naman, just like etong configuration na to. So, your I in here is actually equal now to your BC minus your BBE. Parang dito ka lang din. Over your RE. Kumbaga yung I is actually equal to your IE. Parang si IC lang din yun. IC and then your IE. Okay, for bias stabilization, so the stability ng system is a measure of the sensitivity of the network variations in its parameters. So your beta rather is increasing with increase in the temperature, while your BVE along now to your transistor decreases about 2.5 millivolts per degree Celsius with increase in the temperature. So your ICO, reverse saturation current, it doubles naman yung in value for every 10 degrees Celsius in temperature. So we have variation ng silicon transistors since kaya by default, pag hindi binabang sa problem, we take it as a silicon transistor. So, here is a table kapag minsan di given. So, ito yung gagamitin na values. For device stabilization. At operating temperature, ito na siya. So, take note on this table, memorize it as well. And for the reverse saturation, your beta amplification factor, and then your BBE. O pag fixed bias configurations, yun nga, that your for your reverse saturation current is equal now to your beta. Pag emitter bias configuration, eto dyan. Derive nga for emitter bias. So your reverse saturation current S is calculated beta times 1 plus RB over your RE. Kinuha natin dun yung RB over your BE. Your RE rather is supposed to be RE. Kapag naman your RB over the ratio of your RB and RE is much greater than your beta, so it reduces that your configuration, your reverse saturation current is just equal to your beta. Pag much less than 1 naman, so it's just simply 1. For the range we're in between 1 and your beta plus 1, so it is the ratio of your RB over your RE. Ito yung BE dito that's supposed to be RE. Pag voltage configuration, ito naman po. Ayan. And pag feedback bias configuration, this is how we solve for the stability, your S. Summary for other configurations. Ayan. for fixed bias, emitter voltage divider, and then feedback bias configuration. Kuba stability to based yung kanina dito yung sa stability for the reverse saturation current, and then stability basing for your BBE, and stability basing now your beta calculations. Familiarize lang, ganyan at ganyan, very direct substitution lang din naman for the formulas ng stability, bias stability. Resistor nga. So yung parameters kasi is based on your beta, your BBE, at saka si current. So the formula is taken lang kay Floyd. For the transistor rating, so just like dun sa diodes, so for your ICs is your PD max over your VCE, where your VC is equal to PD max over your IC. So yung product ng VC and IC must not exceed yung voltage from your collector to your emitter, and IC cannot be maximum at the same time. As an amplifier, so meron din tayong for AC analysis with AC input voltage. With AC nga, so ito yung sa waveforms. So, for AC analysis, single stage lang din naman siya. Ganun lang din, parang iti-take charge lang din natin yung sa mga summary. Describing na din naman yung mga output and input impedance. And then your currents dito. So, it's been summarized dito yung sa characteristics for the different configurations for AC analysis. Yan, summary lang. The main advantage for BJT with high power handling capability volts or 500 amperes, sufficiently low forward conduction voltage drop. While its drawbacks of the power ng BJT, yun nga, slow switching, in inferior safe operating area, thus yung over voltage protection is needed, tapos it requires complex so lang, doon lang yung sa BJT. So dito sa FET, consider natin yung types ng field effect, yung relationship between JFET, relationship between gate source voltages and drain current, BJT, range din ng Q points, and advantages and disadvantages. Compare now to BJTs. So, si BJT is yung current control device. So, pag tingnan na natin yung FET, it is a most likely natin tinitignan yung calculation sa BJT. Your input current controls now is output characteristic. While your FET is a field effect transistor, ito naman yung voltage controlled component as well. So yung basic types ng FET is yung junction FET and yung metal oxide semiconductor, yung mga FET, karoon ng depletion. So, ayan. FET is a unipolar. FET depends on holes or electrons. So, unlike dun sa BJT kanina, pwedeng dalawa yung parang binabagi. So, JFET is also a three-terminal device that contains two semiconductor materials and a single junction, just like your BJT as well. At two semiconductor materials, so yung P-type or your N-type. Yung three terminals naman niya are called the source, drain, and the gate. So yung sa katumbas niyan, so we have now your source for the water, and then we have now your gate and your drain. So source, and then your gate, and then your... So just like BJT, so ano naman, so pag sa NPN, so yung tinatawag natin na P-channel. Kapag sa PNP, ito na yung tinatawag natin na N-channel. Kasi yung channel is made up of one type ng material. While yung gate naman is made up of the another. Kung dito yung sa gate. So, pag sa JFET, identify by its channel material, kaya P-channel and N-channel. So, depende kung saan siya made. So, yung gate naman, since it's made from the other material, now yung channel like a belt around your waist. And kung ba dito sa NPN, the two N-type materials are actually ends of the same material. So parehas sila kung saan gawa. So that's your gate, and then dito lang yung sa source. So ano yung katumbas? Kung di ba dito yung sa BJT sana, so yung emitter mo, yung katumbas dyan is your drain. Tapos yung base is your sa gate, and then collector dun sa source. Yan, yung channel. So, the name is based kung saan gawa na material yung sa channel. Either a P-type material or an N-type. Di ba? More positive or more negative kapag dun sa semiconductor theory. Ayan, for the schematic symbol for the JFET, field effect transistor, or your FET in general. So, ayan, pag N-channel siya, kumbaga parang N-channel yung PNP, tas yung NPN ka na yung P-channel naman. So, kung ano yung nasa gitna, yun yung tawag natin dun sa field effect transistor na yun, or FET. For an N-channel, ganito yung schematic. For a P-channel, ganito naman. Parang yun, nakapasok na, or NPN, pasok na pasok, PNP, nakapasok na, so parang palabas na, nakapasok na, so lalabas na, kumbaga ganun. So P-channel yun. So PNP na yun, pasok na pasok, ganun. Ganun yung schematic symbol. So take note. So in the schematic symbol, pwede kasi minsan nilalagay sa gitna, yung sa may arrow or nasa dulo. Pwede sa gitna or sa dulo lang. Ganyan lang naman sa for the JFET. Yung commonly used nung sa symbol kasi, yung arrow is positioned on the gate terminal, always on the gate terminal, or points toward the N-type material. Points toward now your N-type material. So ito pag N-channel, so point towards kung sa type ng material, sa N-type. Ito na point towards kung saan, kung sa material which is your P-channel, P material, positive mga element material. So, source, drain, and gate, katumbas siya is emitter, collector, and then your base. Source dun sa emitter, drain dun sa collector, and gate dun sa base. Diba? Source, yung emitter, drain, yung collector, and base is yung sa gate. So paano din natin i-bias yung JFET? So JFET is always operated with a PNP or your N-channel na type, N-channel type ng JFET. So correct DC bias voltage applied to an N-channel device for conduction, since yun nga yung material sa gitna is an N-type. So your VDD provides now a drain to source voltage, drain to source. So parang ito yung kanina, collector to emitter, parang ganun. Ito naman, your VDD provides now a drain to source voltage, supplies current from the drain to source. So your VGG naman sets yung reverse bias voltage, since operated with VGG at reverse bias between now your gate and the source. So gate to source naman, ito na loop, gate to source. Ito drain to your source loop. Reverse biasing of the gate source function with a negative gate voltage, kaya more negative si gate voltage, produces now a depletion region along now your PN junction, which extends into the N channel and thus increases yung resistance by restricting now the channel width. So parang ninanarrow or widen lang din yung sa may depletion region. So ito yung nangyayari pag at greater VGG, nagnanarrow yung channel, which increases daw yung resistance of the channel, pero it decreases daw your current along from the drain. Kung tinitignan natin, it will narrow yung channel. So parang less na yung depletion region, so magkakaroon ng mas pasok or flow of electrons. While less VGG will widen naman yung channel. It will widen the channel and increases now your current ID for the conduction. So yung basis natin parang ito, binibigyan natin siya ng counter from dun sa BJT, ano. So for JFET characteristic and parameters naman, so ayan, may tinatawag na tayo na pinch of voltage. So we have the ohmic region, constant current region, and the breakdown region. Pag sa JFET naman yung characteristic curve. Stable. So dito sa characteristic curve, you can see that as BDS increases in magnitude, yung current drain current, your ID, also increase. As it increases, your VDS, your ID also increases. So once yung VDS reaches a specified value, which is ito yung pinch of voltage na tinatawag natin, further increase in VDS are offset. So it is now directly proportional increasing in channel resistance, and yung device kung ba nag-constant na siya dito wherein your VGS at 0. So at pinch of voltage, parang ito yung active point, yung constant current region, kaya VGS is at 0. So pag yung VP pinch of voltage is measured kapag at your VGS is already at 0. B pinch off. Kaya pag titignan natin, kung mas simple na nga si JFET than your BJT, kasi parang ito minsan Shockley's equation na lang yung ginagamit, and then just like Shockley's, tapos konti na lang yung sa calculation. Kaya mas mahirap si BJT compared kay FET. is equal now to your BP or your pinch of voltage and your VGS at 0, di ba? At VGS 0, doon tayo nagkakakuha ng your pinch of voltage. So your drain current, pag measure natin yung drain current, it will reach its maximum possible value. Wherein yung maximum value na yung tinatawag natin na shorted gate drain current or your IDSS. IDSS, which is pag sa mga JFET or FETs, yun yung binibigay dun sa specification sheet or IDSS. There. When your VDS now equal now to your pinch of voltage or at operation, when measured nga siya when VG is at 0, along dun sa gate is at 0. So na yung pinch of voltage and your IDSS. While your gate source cut-off voltage, gate to source cut-off voltage or your VGS off, pag VGS off nga, there is a value of your VGS that reduces now your drain current or your ID to approximately 0 ampere. Yun yung VGS nga called at 0 or at off value, VGS off value. So when your VGS is equal to your VGS off, yung depletion region, just like doon sa mga image kanina, yung depletion region, dun sa kulay brown, around the gate closes and resulting now to your ID equal now to 0. Your ID equal now to 0. Kumbaga, it reaches naman your VGS off at a maximum value. So pag observe nyo sa specification tables ng mga transistor, specifically pag FET yan, always that your it could be your BP, pinch of voltage, or your VGS off yung binibigay na ratings ng mga JFET or FET. Since most of the time they are equal in magnitude but opposite in polarity. So only one value is typically listed sa mga specifications. So extending more yung sa characteristic curve nung sa JFET, drain characteristic and transfer characteristic curve ng FET. Observing now your pinch of voltages and then at VGS off. So as we increase along negative, so bumababa until nga mag-0 yung VGS off. Kung ba yung na-explain dun sa mga illustrations. So actually this is observed or represented by yung Shockley's equation dun sa operation ng JFET, where your Shockley's equation is equal now to your ID, solving now your drain current IDSS times 1 minus VGS over your BP. Kaya minsan it is simply your VGS off yung si BP, si pinch of voltage, si VGS off. So it was introduced by William Bradford Shockley, co-inventor ng first transistor and formulator ng sa field effect theory, which is employed in the development ng transistor and even FET. Some other parameters is yung gate resistance and capacitance for the JFET. Pag sa gate resistance, yung gate of a JFET is always reverse bias under normal operating. For this reason, yung gate of the resistance ng JFET is extremely high, typical in giga-ohms range. This high gate impedance is the primary advantage ng JFET, yung gate impedance nga, over the BJT. So it can control larger values. So when the gate terminal of a JFET is used as the component input, so yung high resistance ng gate presents now no load on the source. So calculation now no Rin is your VGS over your IGSS. While your CISS, yung input capacitance, result lang ng JFET operating with reverse bias PN junction. Kaya ang tataas nung along sa gate, kumbaga iniiwasan niya na mag-conduct, parang yung gate never becomes forward bias. Kasi if in case, parang magdadamage siya dun sa component. Okay, for the transconductance, for JFET, so change in current, drain current for a given change in the gate to source voltage. So it is a ratio on the change of the drain current over the change in the gate to source voltage or VDS at constant. And it is measured in Siemens or Siemens. So your YFS or your GMO is actually equal. So pag GMO not given, it's actually value ng GM. So ito, di ba, it is parang yung VP kanina, it is equal to VGS. They are just same magnitude but different, kumbaga, different in this sign convention. So for the transconductance, ito yung sa calculation. Ito naman kapag just like taken at 0, so it is simply equal now to, if BGS is at 0, so it is simply twice your IDSS over your BGS of or your B peak pinch of voltage. Kaya ito naka-absolute value. Most of the time parang negative kasi yung BGS or your B peak. To solve now for the transconductance. So your GM is at max kapag your VGS is at 0 and minimum kapag given siya at VGS off or your BP, your pinch of voltage. So let's try to take an example for that. So the following information is included sa datasheet ng JFET for 2N5457. So typically your IDSS is at 3 milliamperes, your VGS off at -6 volts at maximum, and then your YFS max at 500 microsiemens. Using these values, determine now the forward transconductance for your VGS given at -4 volts, and we find now your ID at this point. So for the ID, so for the forward transconductance, yung GM, gamitin lang natin yung formula kanina. Ayan. And then for your ID, so di ba we have Shakti's equation, IDSS is equal to 1 minus your VGS over VGS off raised now to 2. And given naman lahat, so we can simply solve na yung transconductance for transconductance and then your ID. Okay, JFET biasing circuits. So we have gate, self, and then voltage divider bias. Just like yung sa BJT. Ito madali na lang kasi mabilis lang dito sa FET. At pag gate bias, so yung JFET counterpart is yung base bias, base biasing. So yan nga, ito yung sa configuration for the circuit. And then yung DC base line represents now, and yung red, all of the possible Q point or the operating point ng FET naman for a gate bias. For a gate bias, so equations, your VGS is actually equal now. Your gate to source is actually equal to your negative VGG or your VGG as well. But ito yung sa gate to your source, your VGG. Out solving sa IG. So ID, simple checklist equation lang. Tapos konti na lang yung mga KVL natin na ginagawa. Drain to source naman, VDD minus your VDS, tapos minus your IDRD. Kaya VDS, which is yung parang katumbas ng VCE kanina, is VDD minus your IDRD. Ganun lang. Pag base bias naman, so yung base yung na-apply natin ng external sources along to the base bias. Ayan, ito yung sa configuration. So we have until, meron dun sa gate, meron din dito sa my source, then meron din dun sa drain. So taking now the equations, kung tignan nyo, ID is solved ulit again siya for this, yung shocklist equation. Still your VGS is now equal now to your VGS gate, now to your source. It is your ID times your RS. Yun yung VGS. VDS, so ito lang din. So parang your IC is equal now to your IE din dito. Pero still ID lang yung naman tinitingnan natin dito. Kung ba IG is taken 0 nga, di ba? Kung ba at operation dapat na at 0 siya. So, kaya minsan ID lang yung nasa-solve dito. Kasi BJT, ang dami pong kailangan i-solve na tawag nito na currents. Kaya current control device siya. Ito voltage control. So most of the time sa VGS, given na parang same lang yung current at operation, which is yung ID natin kay FET. So ito KVL lang dito for your VDS. So self-biasing naman, self-biasing now your JFET. So at large RG required to prevent now shorting sa input signal to ground and to prevent now yung loading ng driving stage. So ganun lang din, VGS is your IDRS and then your VD is actually parang subscript convention. Your VD is VDD minus your IDRD. As your VDS drain to your source, so dito lang your VD D, VD dito minus now your VS. So your VS is calculated also ISRS. ISRS, air ID times your RD plus your RS. Since we have done yung sa VD, so your VDD minus that IDRD. Kung ba yung VD na is VDD plus minus IDRD. For this example naman, find your VDS. So direct substitution na lang din. Hindi. Analyze natin dito sa circuit. Find now your VDS. Tapusin lang natin dito sa BJT FET. Find VDS and VGS in a figure for the particular JFET in the circuit. Yung internal parameter. Values given yung transconductance, GM, VGS of IDSS, such that yung drain current is approximately at 5 milliamperes is produced. Another JFET even of the same type may not produce the same results when connected in the circuit due to the variations in parameter. So for the calculations, your VS is simply your IDRS, as yung VDD, VD minus your IDRD. Given naman na yung ID at 5 milliamperes. And direct substitution na lang. So your VS is IDRS, which is ID 5 milli times your 220, and then your VD, para masolve yung VDS and VGS, so your VD is VDD minus IDRD. 15 minus your ID times your RD. Tapos, to solve now your VDS, drain to your source. So, yung nasolve na natin na VD minus now your VS, which is IDRS. So doon. Tapos yung VGS is dapat at VG equal now to 0. So, simply, VGS, your VG at 0, and then minus na your VS, which is IDRS. Ayan lang siya. Setting now yung Q point ng JFET. So, yung at Q, yung mga QQ, VGSQ, VDDQ. So, the operating point ng JFET, we determine first yung ID, shocklist equation lang, for a desired value ng VGS, either by using transfer, characteristic curve, or yung shocklist equation. Mas madali siya shocklist equation. Then, calculate natin yung RS, which is VGS over ID, and then for midpoint bias, midpoint bias, ito yung ginagamitan na 0.5 sa IDSS, or make now your VGS equal to your VGS of over 3.4. And to set now along your ID, so 0.5 lang nung sa given na VDD, and then pick RD equal to VDD over twice your ID. ID solved siya sa Shockley's equation. So we determine yung value ng RS required to self-bias a P-channel JFET. So given, sinasundan lang din natin. So we solve ID. Given na tayo ng IDSS, we have VGS of your B peak at 15 volts. And your VGS is 5 volts. So through Shockley's equation, we can solve now your RS, which from dito, VGS over ID for setting now the Q point. So through Shockley's, and then we have now your RS, VGS over your ID. Pag voltage divider, so ganyan din ang voltage divider, ganun din, parang solve tayo ng VTH and RTH. So solving now your VG, parang dito, your VG. So it is your VDD times your R2 over the sum. Tapos, while solving now your ID, ito different kasi solving your ID, it's not through your Shockley's equation. So parang nag-KVL tayo dun sa equivalent na Thevenin's or yung sa converted. Wherein parang dun tayo, dito tayo nag-KVL. Pag nakuha natin yung VG, so we have now your VG minus your VGS, gate to source, parang ito yung BBE din, VGS yan. And then, minus your IDRS. Tapos dito yung VDS naman, kuwan lang, KVL along this drain to source na loop. So for a voltage divider bias, to keep now yung gate source junction reverse bias, it should be that your VS is much greater than your VG. Kaya nga, dun sa general or sa assumption na VG is taken at 0. So your VS is IDRS or your VG. Well, yan din, same lang din naman yung napakita niya ditong formula. Okay, for a voltage divider, try nyo na lang, ganun lang din naman. Dali na lang, susundan. Pag na rin to sa graphical, ganun at ganun din naman. DC load line, madali na lang. Okay, Q point stability. Just like dun sa mga BJT kanina. Pero ito, at operating lang. So through the characteristic curve. Okay, the basis na natin dito is yung JFET. So, at nagkaroon nga lang ng metal oxide. So, just to address yung mga problems with yung sa JFET. Pag metal oxide semiconductor FET, so differs from JFET that has no PN junction. Yung gate ng MOSFET is insulated from the channel by a silicon dioxide layer. So, doon na base na yung sa pangalan. Tapos two basic types ng MOSFET is yung depletion nga and the enhancement. Dahil doon sa insulated gate, these devices are sometimes called IGFETs, insulated gate FET. So on the construction ng depletion MOSFET, so your N-channel D-MOSFET is usually operated sa depletion mode, kaya depletion MOSFET, wherein your VGS is less than 0. And in the enhancement mode, so yun naman, VGS, your gate to source is actually greater than 0. And here is the schematic symbol pag sa depletion. P-channel D-MOSFET uses yung opposite voltage polarity. O opposite voltage polarity. Okay, depletion enhancement MOSFET. So negative gate voltage applied to an N-channel depletes now the channel of electrons, thus increasing yung sa resistivity. Pag enhance, so yun nga, VGS greater than 0. Electrons are attracted into the channel. Increase naman is kaya nga enhance yung channel conductivity. Ganun lang. So, ito naman for enhanced MOSFET, ito yung sa schematic symbol. Tapos, E-MOSFET simply operates now only in the enhancement mode. So, pag sa P-channel, yung negative gate voltage above a threshold value induces now a channel by creating a layer of positive charges in the substrate region, silicon dioxide layer. Channel conductivity increases with VGS. So as it increases, so yung channel conductivity also increases since it is for VGS greater than 0 pag sa enhanced MOSFET. Other MOSFET, pakibasa na lang. Marami pa kasing nangyaring variations or models yung mga MOSFET. Kumbaga, depende lang dun sa mga nagagamit minsan na material, yan, power enhancement, and through its operation. A double diffuse transistor na MOSFET, gallium arsenide naman, GAAS na FET. There, so mas simple lang talaga yung sa may FET compared dun kay BJT since kay FET most of the time shockless equation lang yung ginagamit tapos sa voltage divider lang nagkakatalo. Questions? Okay, if wala, schedule natin yung sa next topics for next meeting before I can proceed naman dun sa third, sa logic circuits and computer fundamentals. May questions po?
None, sir.
Siguro kung kaya ko this hapon, pwede tayo sa ECE. I-discuss ko din sa inyo yung first topic, semiconductor and diode since ako na mag-take ng elect talaga. Kuha na lang ni Sir Joel later on transmedia. Ako din mag-go wireless. Sa EE naman, last ko na ata sa inyo, telecom electrics yung sa computer systems and microprocessors naman. Pwede ko din kayo pagsabayan actually ECE and EE sa logic circuits since ako na din take naman doon. If no questions, so ayun. Thank you. Good day and take care.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Sir.
Thank you, sir. Bye, sir.